Right, so just to quickly recap what we did last lecture. We talked about climate changes that occurred over relatively long time frames, so less than 1 million years, but longer than a few thousand years. So this is the kind of idea that at the top here, you've got some maybe changes in the orbital parameters of the Earth. So in this case, the green is precession, and the blue is obliquity or axial tilt. And that results in some change in the amount of solar radiation that's being recorded or being received at the Earth's surface. This is what this figure is showing in the bottom. So the color on here is the amount of solar radiation each latitude gets in the summer. Okay, so you can see that these changes in the orbit cause there to be changes in. So sometimes it's a bit warmer summers, sometimes the summer's a bit cooler. At different latitudes. So this is the equator down to the South Pole and then up to the North Pole. And you can see from this that when we have cold or less solar radiation arriving in the summer of northern hemisphere, okay, so that's the blue there, we tend to promote, I'll just give myself a pointer so you can see the pointers. You tend to promote glaciation, so the climate gets colder. So when we have less solar radiation in the high latitudes, we have this cooling climate. And that's what's thought to explain the timing of these climate variables, this variation, as we go into this icehouse world, getting colder and colder and colder. We have these glacial interglacial cycles that flip backwards and forwards, recorded as oxygen isotopes. And the key thing is that the magnitude of these changes, so these are the various different orbital forcings caused by changes in the Earth's orbit, is actually quite small. So to explain the magnitude of the variability, so to make the size of these glaciations, you have to invoke some kind of feedback. And the ones we discussed were the feedback of albedo. So when it gets cold, we get more ice. Planet's more reflective, gets colder, which promotes more coldness. And carbon dioxide. So carbon dioxide is more soluble in a cold ocean, so that means the atmospheric concentration will go down, which makes it colder, which means more will dissolve in the ocean. So that acts as a positive feedback. Okay, and we can explain those using that equation up there, which we all know and love. We then went on to talk about short-term climate variability. So this is on a maybe just 1,000 or hundreds of years timescales, but very, very rapid changes. But it's not the global temperature, we're just redistributing heat between the north and southern hemispheres. And that's driven by internal climate cycle, internal climate dynamics. So we discussed those in that lecture. And then also we discussed this concept that the climate is not linear. So it can switch rapidly from one stable state to another stable state if you change the forcing gradually. So this is this kind of threshold approach of, threshold response, sorry, of climate. Okay, so today we're going to be talking about even shorter timescales. Okay, so some of the mechanisms that control climate on the kind of timescales of human interactions. So this is the kind of one of the main plots for today. So this is a temperature reconstruction based on thermometers. So these are actual measurements of temperature measured all around the globe, averaged together in some way to get the global average temperature. And you can see here from the beginning of the 20th century to basically 2015, which is this data point up here, we've had approximately 1 degree Celsius of warming already. Okay, so 0 is kind of arbitrarily fixed at this point in the 1960s average, I think, or 1950s to 60s average. So we start off at kind of like -2 and go up to 0.8. So this is the temperature anomaly. This is not the actual temperature. But we can see that we've experienced quite a lot of warming over this time period. But one of the things we're looking at today is what are the reasons for this warming, and also what are the reasons for some of these variability. So it's not just a nice monotonous straight line. We have some variability in here. We're going to see if we can explain some of that. Okay, and we're going to try and do that using kind of the parameters in this equation. So changing the solar flux, changing the albedo, so the shininess of the planet, and changing the emissivity of the atmosphere, so changing the greenhouse gas effect. So those are the only things that can really affect the global temperature. So let's go and have a look at them. So first of all, the sun. So if we look at the sun, and people have been looking at the sun for well, forever, basically, since we've had eyes. For, I guess, for 500 years, something like that, we've been looking at the sun and we've been noticing these things called sunspots. So these are these basically slightly darker patches on the surface of the sun. And people write them down because that's what they did back in the Middle Ages. And I thought, oh, that's interesting. And we've carried on doing that to the modern day. And it turns out that when we have these sunspots, the sun is in a more active phase. So it's basically the sun is giving out more energy. So that makes the amount of energy that's received at the Earth's surface more, so we should get warmer. And it has this really characteristic 11-year cycle. So the sun basically every 11 years goes through this cycle of being a little bit more powerful, a little bit less powerful. So one of the questions is some of this variability, some of this up and down, wiggle, 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 yeah? Is that caused by the variability in the power of the sun? Okay? Could all of this be explained by the variability in the power of the sun? So one of the things we need to do is we need to test this kind of hypothesis that the sun is responsible for all of this. So one thing we could look for, in these data is, do we see evidence for that 11-year cycle? Okay? And if you look at the data, well, maybe a little bit, but it's certainly not as obvious as the forcing was. So if we look back at the forcing, see that's got a really nice regular up, down, up, down, up, down. And also there's not much of a trend on these data. So from the 1950s to 2000, there's no increase in the overall solar activity. So solar activity can't be responsible for the overall trend here. And also, the 11-year cycle isn't so obvious in the temperature data. So the sun's power is changing, but it's not appearing to affect the climate by much. Okay? And we'll see why that is tomorrow. Another thing that can affect climate are volcanic eruptions. So we talked a little bit the other day about how when you've got more volcanic eruptions, you give out more CO2, and this increased volcanism at this point, basically back in the early Neogene, that was responsible for perhaps some of the warmer climate back then. And the reduced volcanism since then, we mean less CO2 in the atmosphere, a bit more cooling. So that's not the only gas that volcanoes give out. So on very long time scales, millions and millions of years, the CO2 given out by volcanoes, that's what's important. But on short time scales, so this is the Eyjafjallajökull Icelandic volcano that went off a couple of years ago, ruined all of our holidays. So you can see that there's all this ash coming off this volcano here, right? So volcanoes give off a lot of ash when they erupt into the atmosphere. They also give off a whole bunch of other gases than CO2. So especially things like sulfur dioxide, hydrogen fluoride, HCl, okay, all of these other gases. And these gases and the particles that come out of the volcano do have an effect on climate. But they only have an effect on climate over a very short time scale. So while the volcano is erupting and maybe for a few years afterwards. And the effect is that they basically, if you have sulfur dioxide being pumped out of your volcano, and that's one of the main gases that comes out of volcanoes, sulfur dioxide, water, that reacts with the oxygen in the atmosphere to form sulfate rather than sulfur dioxide, and that sulfate reacts with water to become sulfuric acid. And sulfuric acid has a very, very high boiling point. Okay? So this means that it condenses very, very quickly into lots of small droplets. Okay? So these small droplets lead to the formation of more clouds, and we'll go on to explain why this is. So what effectively we're doing here is we're changing the amount and the type of clouds, so we're making the planet more reflective when we have a volcanic eruption. So this only lasts for a few years after the volcano, but it's much more effective than the CO2 that the volcano gives out. Okay, so it means that when volcanoes go off, when big volcanoes go off, we tend to have a cooling effect. So the reason this is imagine these boxes represent kind of bits of atmosphere. So if you had, let's start up here, if we had basically a box of atmosphere full of moist air, lots of water in it, and we start to maybe cool down that box, and we basically want to start forming water droplets, those water droplets can't form unless there's something for them to start basically precipitating out onto. So what happens is that the little parcel of atmosphere gets super saturated, so it's got too much water in the gas phase, and it wants to precipitate that out into, or wants to condense that out into water droplets, but it can't do it because there's nothing for the water to kind of condense onto. So what happens then is you reach a state where you all of a sudden precipitate out all of your water in kind of basically one big go, and you end up with quite big drops of water. Okay? Whereas if you had lots of particles in the atmosphere, lots of dust, or lots of little tiny bits of sulfuric acid, as soon as you start to lower the temperature, the water can condense onto those little droplets, which means you start off with lots and lots and lots of very small droplets of water. Okay? So then as you cool the gas down some more, you want to precipitate out some more water, it's already precipitated out as droplets. So you end up, if you have lots and lots of what we call cloud condensation nuclei, or basically particles of dust, or bits of volcanic ash, or sulfuric acid droplets, you end up with clouds that are made up of much smaller droplets. Okay? Whereas if you don't have those cloud condensation nuclei, you have clouds that are made of much bigger droplets. So this has two effects. So if you have smaller droplets in your cloud, it makes the cloud appear whiter. Okay? So if you have big droplets, it appears darker, which means that if you don't have the cloud condensation nuclei, your albedo is lower. So that means you have a warmer planet. If you have these smaller droplets, the clouds also last for longer. Okay? Because these big droplets fall out of the sky as rain. Okay? So this means that after a volcanic eruption, the clouds in that bit of the atmosphere will be whiter, there'll be more of them, and they will last for longer. So that makes that bit of the planet more reflective, which affects the albedo, and we get cooler. So this is what happened to the sulfur dioxide concentration in the atmosphere immediately after the Mount Pinatubo eruption. So Pinatubo is in here somewhere, I think. Up in Indonesia. Anyway, it's in there somewhere. Where is it? Oh, it's in the Philippines, of course. Fucking idiots. It's not in Indonesia. Yeah, so it's up there. Anyway, so it went off and sent this big cloud of volcanic aerosols all the way around the planet. And that meant that this whole region, okay, although there were already clouds there were more clouds there, okay? And importantly, it happened near the equator, which meant that the volcanic aerosols could get into both hemispheres. So it had a dramatic cooling effect on both hemispheres. So other things that affect how effective volcanoes kind of are. So if we can look at some volcanoes, so this one, Fuego, which is in Central America, I think. See, that one kind of put lots of particles into the atmosphere, and it took a long time for those particles to come out of the atmosphere. Whereas a volcano like Mount St. Helens, which erupted in 1980 something or other, it was definitely in the 80s. Anyway, that erupted, had much more in the atmosphere initially, but it came out much more quickly. Okay, so these particles basically that are in the atmosphere, they only stay in the atmosphere for a very short amount of time before they're washed out of the atmosphere. So where the volcano happened, so Mount St. Helens happened at quite high latitude, okay, where atmospheric circulation is basically descending, and there's lots of weather, lots of rain at this latitude, so that washed out the particles from the atmosphere, whereas these more tropical, El Chichon, which was in Mexico, these eruptions stay in the atmosphere for a lot longer because they're near the equator where atmospheric circulation is rising. Okay, so this stuff can stay up in the stratosphere for longer. The other thing that determines the magnitude of the climatic effect is the amount of sulfur in the volcano. Okay, because the main cloud condensation kind of nuclei effect is from the sulfuric acid rather than from the volcanic ash. So what we've got here is basically an estimate of the amount of sulfur that was erupted in the volcano, and this is basically made from measurements of inclusions of melt inside crystals. So this is basically a sample of the melt, the magma before it erupted. Okay, it's basically trapped inside minerals. We can measure the sulfur content in that, and we can measure the sulfur content in the rocks that are erupted, and kind of do a mass balance and work out how much sulfur is missing. That must have been kind of degassed during the eruption. Okay, and then we can compare the amount of sulfur that was erupted to the global temperature change, okay, for that year that the volcano erupted. So you can see for Mount St. Helens, a relatively small eruption, okay, you get 10 to the minus 1 degrees C, so 0.1 of a degree Celsius cooler. For large eruptions, Krakatoa, okay, we might get half a degree C of warming. For very, very large eruptions like Laki in Iceland, Tambora, we might get a whole degree Celsius colder for that 1 year. Okay, we've got this mechanism now, and we can kind of think, well, if we have volcanoes go off a lot, that might make the planet cooler. So what we can do now is test that case with a longer-term climate record. So what we've got here is some measurements from an ice core. So this is basically a little chunk of ice core, and what it's doing is being melted at the base, and then they're just measuring the chemistry of the water that's given off as the ice melts, and you melt through year by year by year. You might just be able to make out here, there's this layer, this is an ice core that looks a bit dusty. So what this is doing is it's basically looking at the products of volcanic eruptions that are a long way away, get blown over Greenland, okay, and that we get some record of the acidity of the ice. So this is basically how much sulfate aerosol is being deposited on Greenland, and that's a proxy for how much volcanism there is. So an indirect measurement of global volcanism, or at least northern hemisphere volcanism. So you can see these regions here when so increasing acidity is that way. So we have more volcanoes going off here, fewer over here. And then we can compare that with an index of temperature, so probably some other proxy measurements, maybe the isotopic composition, because we can't directly measure temperature back in time, so we use a proxy measurement. And you can see when we have fewer volcanoes go off, it's warmer. When we have more volcanoes goes off, it's cooler. So this kind of fits in with our theory that the amount of volcanism going off on very short time scales can cause cooling. So that's a little bit of a side. You get the same effect when you have a meteorite impact. So when a meteorite hits the ground, you kind of like splurge out a whole bunch of rock and dust and stuff like that. And depending on what kind of rock the asteroid hits and what the asteroid's made of, you can also inject lots of sulfur into the atmosphere. So asteroid impacts have the same, or thought to have a similar kind of effect as volcanism in terms of a short-term cooling. So this is the idea that perhaps kind of larger events that also had climate impacts. We can also use the same kind of theory of using sulfate aerosols to affect clouds to maybe do something about the climate of the planet. So this is the idea that we might be able to pump sulfuric acid up into the stratosphere and maybe form more clouds in the stratosphere, kind of by geoengineering, and that will have the effect of cooling the planet and mitigating some of our anthropogenic warming from CO2. So not saying that this is necessarily a good idea, because there will be other effects from this, and there are also issues about the political governance and the ethics of doing this, but it would work. So it would cool the planet, wouldn't be that expensive, maybe a couple of billion pounds a year to do that. But it's an idea that's out there. So what we can do to test whether these volcanoes, going back to what kind of we're supposed to be doing, is we can see if the forcing that we predict from all these volcanoes going off over the 20th century, and we know when the volcanoes were going off because we were there, that's a big volcano. So what we've got here is a plot of what we think the total climate forcings were. So this is from the whole of basically the 20th century. So the green line is the forcing that we would get if we were only considering our greenhouse gas emissions. And you can see that's basically being smoothly going up through time. You can see this little orange curve. This is this 11-year wiggle from the solar flux changing. And you can see that the magnitude of that solar variability is actually really, really small. So although the power of the sun has been changing, it's not been changing enough to explain kind of the majority of climate change over the 20th century. Other things on here kind of explain up there, so changes in things like land use and the reflectiveness of snow and stuff like that. But the ones I want to look at here are these kind of curves down here. So this spiky thing here is basically what we would expect the climate forcing to be if a big volcano went off. And we know that, so this was, that was Krakatoa, I'm not sure which one that was, but we've got Pinatubo here, Mount St. Helens, and one of the El Chichons there. And these big eruptions have gone off, and we expect there to be cooling, so a negative radiative forcing with those. So we can add up all of the forcings, okay, and that's what this curve is at the top. So there's this overall upwards trend, okay, and but with these occasional little spikes down. And you might be able to just kind of with the kind of a little bit of squinting and whatnot, you can kind of match up kind of some of these kind of negative anomalies in temperature do coincide with times when we had these volcanoes go off. So some of this wiggling up and down might be due to the atmospheric aerosols from these volcanoes. It's clear that we're not fully describing, so this curve doesn't look quite exactly like this curve. So something how we convert the amount of volcano going off to a climate forcing, we're not quite understanding that 100% at the moment, but we are at least showing that there are climate changes that last a couple of years that are caused by these volcanoes going off. Okay, so we'll talk a little bit about this type of slide tomorrow, but this is basically showing that if we want to explain the warming that we've had, so here we've basically got the grey splodge in the background is our best estimate of the reconstructed temperature over the last 1,000 years based on proxy records, mostly tree ring reconstructions. And you can see the coloured lines on here are basically climate models trying to reconstruct those temperatures. And there are two groups of models. You've got ones with the thick lines and then the ones in the thin lines. Okay, so these are the thick line ones, these are the thin line ones. And the difference between those two groups of models, so they're basically just running different versions of climate models run by different labs to see how repeatable the modelling effort is. There is some scatter there. But basically, the models at the top, the thick line models, are using all of the forcings. Okay, so they're taking into account the radiative forcing from volcanoes, the radiative forcing from changes in solar output, and they're also using the greenhouse gas forcings, which are these lines here. Whereas the models which are in the thin lines are using all of the models at the top, all of the forcings at the top, except they're excluding the greenhouse gas forcings. So the idea here is that to explain past temperatures, you can do really well for the most of the last 1,000 years if you just ignore greenhouse gases, or the change in greenhouse gases, sorry. But for the last bit of this graph, you have to include anthropogenic greenhouse gases to explain the temperature change. So that implies that temperature change has been caused by the greenhouse gases. Okay, so one thing we could say is, have we explained all of the variability now? So the overall trend in this data series is largely due to our greenhouse gas emissions. Some of the wiggles might be due to solar forcing. Some of them might be due to volcanoes. I'm paying attention, don't worry. But have we explained every little wiggle in this curve? And I would argue that there's still quite a lot of variability there that we don't really understand. So moving on to what happened last year. Okay, so last year there was a really large El Niño event. Does that sound like something that some of you have heard about? No? So an El Niño event is basically an internal climate oscillation that happens mostly in the Pacific. And so we'll start off with how it was first kind of investigated. So two places, Tahiti and Darwin in Australia. Tahiti is in French Polynesia, not Australia. And if you look at the atmospheric pressure at these two places and kind of like normalize them to the average atmospheric pressure at that site, you can see that when there's high pressure in Darwin, there seems to be low pressure in Tahiti. High pressure in Darwin, low pressure in Tahiti. And they seem to be completely opposite to each other. So there does seem to be some coupling of atmospheric circulation between these two sites. So they're very closely related to each other, although they're a long way apart. And you can basically come up with this index of the pressure in these two places, and basically because people have been measuring atmospheric pressure at these sites for a very long time, we can come up with this really long time series of when high pressure is in Tahiti, lower over Darwin, and low pressure in Tahiti and higher over Darwin. Okay? And we think about, well, what does that mean in terms of how the atmosphere is configured at these times? So I've got normal conditions here, but you could see from that plot there was no normal state. It was constantly flicking backwards and forwards between one and the other. So under normal conditions, the wind blows along the equator mostly from east to west, and that causes all of the water to pile up on the western side of the Pacific. Okay? That makes that region of the ocean very, very warm. That promotes atmospheric circulation to rise there. Okay? So rising atmosphere causes there to be low pressure over that side of the Pacific. Okay? Whereas you get descending air over the rest of the Pacific, so that implies higher pressure. Okay? So this kind of mode of atmospheric circulation leads to this pressure difference between Tahiti and Darwin. And it also impacts the ocean, is that it moves all of the warm water over to one side of the ocean. And you can kind of see that here. Okay, so this is a map of how the ocean temperatures, as they were in 2014, you can see all of the warm water is really piled up over this side. Okay? So we're going to flick forward now to 2015. Okay, so this is the temperature of the ocean in 2015, and you can't really see much of a difference between the two, right? Okay, because we're looking in absolute temperatures. But if we now take these two maps and take one away from the other to see how much 2015 was different to 2014, okay, we get this map. So this is basically the temperature difference. So you can see now that the warm water that was kind of over here has now moved more over to the East Pacific. Okay, so this is known as an El Niño event because it kind of used to be thought that it kind of happened only at kind of Christmas time, and that was kind of when the boy arrives in kind of this heavily kind of Catholic group of countries over here, and it was an event that was particularly important for them because when all this warm water kind of rushed up and kind of went over along the coastline of South America, that had a really big impact on the local fisheries. Okay, so basically all that warm water stopped the cold water upwelling from the deep, which has all the nutrients in, so it meant the fisheries kind of collapsed around this time. So this was a very bad event for these people, and it's a very bad event for them now as well, for a whole bunch of reasons. And we'll come on to those. But effectively what's happened is this warm water pool has moved from being only over on the west to kind of more centrally situated in the Pacific. And that's caused this atmospheric circulation to move. So now the rising air is more over in the middle where Tahiti is. So we have low pressure at Tahiti, higher pressure over in Darwin. Okay. So if we look at the two maps in kind of some detail. So this is how it was in 2014 over here. So I've put 2012 for some reason. I guess that was a full La Nina. So La Nina is the opposite state to El Nino. So before I put normal conditions, okay, so that's really La Nina conditions, but I mean, these are just words that have been used to describe these two end-member states. So La Nina is when all of the warm water is over in the west. El Nino is when it's kind of some of it allows to slosh back over to the East Pacific. And you can see here that when we have this El Nino state, we have this anomaly of warm water over in the Eastern Pacific. Yes, thank you. It's west and east. It can't be that hard to remember. God, right. Okay, and this is a cartoon of an event that happened. This basically pool of warm water building up in 1998, which was kind of the last time we had one of these really big El Nino events. So this meant that large parts of the ocean were a lot warmer than usual. This had drastic effects for things like coral reefs. So coral reefs don't like it when it gets very, very warm. They expel all of their symbiotic zooxanthellae algae, so they bleach, go white, makes them more susceptible to dying. It has widespread climatic implications. So this is kind of what kind of extreme weather we might get when we have an El Nino. So if we make this region of the ocean here a lot warmer, that means there's going to be more rain over this side of the ocean and also over South America. So you tend to get lots of flooding, flash floods, lots of huge rainfall in South America. You tend to get droughts over in Indonesia and the Philippines, where Mount Pinatubo is, apparently. So you get things like lots of forest fires, lots of kind of dustiness, badness. You have huge crop failures in Australia because it's too dry. And similarly in a La Nina year, when all of the warm water is over here in the Western Pacific, you have flooding, extreme rainfall events over in the west, when you have droughts over in the east. So over the last kind of 5-10 years, there's been this real problem in America, particularly in states like California, where there's not been an El Nino in a long while, and they've been suffering from a long-term drought. Okay, so last couple of years when there was an El Nino, they're like, yay, water, and then there was lots of flooding and lots of people had their homes washed away, which was terribly bad. So just like with the atmosphere, okay, we can basically make an index of how El Nino-y the climate has been through the past. So rather than just use atmospheric pressure, we can use measurements of the sea surface temperature. So we basically divide the ocean up into some boxes and say, what's the average sea surface temperature in that box, either measured by a satellite or measured by ocean buoys that are out there measuring temperature. And we can get a time series like this. So we can see that the climate's basically switching backwards and forwards between that bit of the ocean here being warm when we're in an El Nino year and then cold when we're not being in an El Nino year. So this was the event in 1998, which was kind of the last really big El Nino event. The one in 2015-16 is just off this chart. It's kind of almost as big. So why does this matter? Okay, it matters because it affects the weather and kind of hazard from climate change and kind of storminess and all that kind of stuff. But if we actually look now at how it's affecting the wiggles in our climate. So what we've got at the top here is that El Nino index. So when the ocean's warm in the Eastern Pacific, we have a positive anomaly in temperature. So these are El Nino years, La Nina years, El Nino years. And then if we actually look at the temperature of the whole planet over this period, so just zooming in on this little bit here, okay, so this is climate going up, down, up, down, up, down. Ooh, I wasn't expecting it to do that, but it does do that. But if you kind of match up these things now, you can kind of see that when we have an El Nino type period, we tend to have warmer than average climate. And when we have a La Nina, it's cooler than average. Okay, so that's what I was kind of expecting to see, but I didn't realize I did that animation. Oh, look at me. So if you look at the whole world now, and look at the anomaly in ocean temperature, when we have a La Nina year, we have some regions which are kind of warmer than average, some regions that are colder than average. But when we have an El Nino year, we basically make a large part of the ocean much warmer than it would otherwise be. So we're not adding or taking much heat into or out of the ocean. We're just spreading out this warm water that was in the Western Pacific over a much wider area. And because the ocean is very big, okay, this has an effect on the transfer of heat between the ocean and the atmosphere. Because if you remember back to the first lecture, the atmosphere is heated from the surface of the Earth, mostly. So this means that if we make a large portion of the surface of the Earth a bit warmer by spreading the warm water out over a wider area, that means that we're going to heat up the atmosphere a bit more. So that's why in El Niño years we tend to have we tend to have warmer years. Okay, so that I'll do it again. So this hopefully means that we can now explain most of the variability in this record. So we can explain the long-term trend is mostly due to CO2. Some of the wiggles are due to a combination of the solar forcing changing a little bit, okay, but much smaller than it might cause maybe much variability. When a big volcano goes off, we get an anomalously cold year, but when we have switching between El Niño and La Niña, that explains the majority of the variability of the global temperature. Okay? So this is why 2016 and 2015 have been record warm years, because the climate's gradually warming, but we've also had an El Niño event. So I would expect that 2017 will not be much warmer or warmer at all than this year. We'll probably go back down. If we go back down into a La Niña state, we might go back down into one of these. So imagine this was 2016, we might expect 2017 to be down here. The overall long trend over kind of decades will be carrying on to warm, but the year-to-year variability is strongly dependent on whether we've had an El Niño or not. Right, so that's the kind of important stuff from the terms of explaining the rise in temperature across the 20th century. So we're going to go and do a little bit now in terms of in investigating where some of these anthropogenic forcings have come from and why we know they're important. So, so most people are pretty comfortable knowing that CO2 is a greenhouse gas, hopefully. And you can see in the top figure here, this is a record of the carbon dioxide concentration in the atmosphere through time. So the actual measurements of the atmosphere are this tiny little line up here. And all of these symbols along here are measurements from ice cores. Okay, so basically, I think that might be a combination of measurements from ice cores and some of the really early measurements where people were figuring out how to measure CO2 in the atmosphere by kind of just grabbing a bit of the air outside their lab and measuring it. And you can see here that over the last 1,000 years, the atmospheric concentration has been relatively constant. And then as the Industrial Revolution kicks off in the 19th century, we start increasing in concentration, and then 20th century just goes crazy. Okay? So it's not just carbon dioxide. So there are other important greenhouse gases. Methane is one of them. So methane, much lower concentrations. So these are in parts per billion instead of parts per million. Similarly, kind of kick off around the same kind of time in the Industrial Revolution, but increasing much more in the 20th century. And then nitrous oxide as well. So nitrous oxide, even lower concentrations. So these are still in ppb, but we're maybe 5 times less than methane. And you can see those kind of kicking off up there. So those are 3 greenhouse gases that are all important because, first of all, CO2 is kind of the highest in terms of concentration. But methane and nitrous oxide are more effective greenhouse gases. So for every mole of methane and every mole of nitrous oxide, you get a lot more warming effect. And we'll come on to see the exact magnitudes of those later. But it's not just, we've not only been kicking out greenhouse gases. So when we had our Industrial Revolution, we burnt a lot of coal. That coal also had a lot of sulfur in it. So that sulfur got up into the atmosphere and added to our sulfate aerosol loading. So that's kind of marked down here, and you can see this big spike in the amount of sulfur. So as we've been actually cleaning up our act and burning less coal and making sure that the oil that we burn is maybe lower sulfur, we put kind of some sulfur traps on some of our power stations to remove the sulfur. And the reason for that is because it's a big component of acid rain, which is bad for all kinds of other reasons. But you can actually see that's just started to decline now. So the amount of sulfur we put in the atmosphere is declining. And that's kind of a double-edged sword. So that's good. We have less acid rain. We'll see in the next, my last part, that's important. But it means that, so all of these sulfate aerosols will have had a cooling effect on the climate because they're adding to the cloud condensation nuclei. They're making the atmosphere more reflective. So a little bit of this has counteracted some of our greenhouse gas warming, okay? And then when we take this stuff away, because these chemicals don't last very long in the atmosphere, whereas the other greenhouse gases do last very long in the atmosphere. So when we stop emitting carbon dioxide, that will stay in the atmosphere. Whereas this short-term cooling effect, that will just kind of go away. And we'll then get extra warming, which we've already committed to, but have then taken away the mitigation effectively by putting that stuff in there. So this is a tediously long table of all of the greenhouse gases, which are kind of important. It's a little bit out of date now in terms of the concentrations. So we were at, this is 2005, so only at 380 parts per million of CO2. We're now at 401 and a bit. But you can kind of see the important thing in this table is this column here, so the radiative forcing. So you can see here that some gases like CO2, you've got quite a high concentration, so maybe 400 parts per million. That's responsible for kind of most of the warming, so 1.5 watts per square meter of radiative forcing. But some of these other gases, which are in really tiny, tiny concentrations, so parts per trillion, so very, very low concentrations. But they still have, in some cases, a significant, particularly some of the CFCs, because their chemistry is such that they are really, really effective greenhouse gases. Okay, so just looking at the budget of what we've been kind of like doing in terms of putting stuff into the atmosphere. So this table has the top number is how much extra carbon has gone into the atmosphere. So in the 80s, 90s, and kind of 2000s. We can see that we're increasing the rate that we're putting carbon into the atmosphere. Now, that's because we're burning more fossil fuels. So if you look at these numbers here, so the amount of fossil carbon dioxide, this is basically how much coal and oil and gas we're burning, that's also gone up. Okay? But the key thing is these numbers here of how much we're emitted is less than the amount that's in the atmosphere. Okay? So in some cases, it's like about half. Okay, so we've burnt a lot of fossil fuels, created CO2, but only half of it is in the atmosphere. Okay, so that means that the rest of it must be somewhere else. Okay, we can't just magic it disappear. And where it's gone is a little bit uncertain, but we've got some fairly kind of good ideas that quite a lot of it has gone into the ocean. Okay, because carbon dioxide is a gas that's soluble in seawater. So if you increase the concentration in the atmosphere, some of that gas will dissolve in the water. Okay? And we'll see what effect that has on things like ocean pH in future lectures. Okay, so some of it's gone into the oceans, and then that only leaves one other place for it to go, and that we think is into the land biosphere. So into things like forests. So we really don't know that flux very well at all. So the best estimate of that flux is basically taking this number, which we know well because we've kind of added it up by counting how much fossil fuel we've burnt, and that we've not been very good at counting how much fossil fuel we've burnt. We can measure how much is in the atmosphere very, very accurately. We can kind of measure how much is in the ocean. It's a bit harder to measure than the global atmosphere, but it's doable. And then we just, whatever's left over, we assume has gone into the terrestrial biosphere. And this is kind of it's quite surprising really that the land biosphere has taken up carbon dioxide over the 20th century. We've put more and more carbon into things like forests, rainforests, that kind of thing, because we've been kind of cutting them down quite a lot, right? So over this time period, we've cut down lots and lots of forests, which tends to remove the carbon, both in terms of the carbon that's in the wood, but also the carbon that's in the soil. So this does kind of suggest that the forests that have left over have become even much more efficient at growing and becoming greener and storing more carbon. So it's one of the really big areas of research in this department is to try and quantify how forests and savannas and places like that will respond to kind of future climate change in terms of carbon dioxide, in terms of temperature, in terms of wetness, and how these will affect the future of this ability of the land to take up this carbon. Because at the moment, it's a really important sink. Okay, we're putting lots of carbon into these forests, we think, we really hope. And if the forests get to a state where they can't cope with that anymore, if it gets too warm or too dry, they start burning, then the rate at which we're going to be putting the atmosphere concentration will go up will more closely match the rate that we're actually pumping it out. Okay, so that's an important point. So if we just look at a little bit about how our emissions are apportioned, or what actually affects the climate. So this is an old figure. I think I'll flick forward to this. This is a slightly newer figure. It's still kind of 5 years out of date now. But you can see here, so for CO2, that's the biggest bar in terms of warming effect. Okay. The next most important gas is methane. Okay. But methane is not just a greenhouse gas. Okay. It kind of acts as a greenhouse gas, and then it gets converted into carbon dioxide by being oxidized. So that gets rid of the methane, which is good because methane is a stronger greenhouse gas than carbon dioxide. But it does mean that you then add carbon dioxide and kind of other reaction products into the atmosphere by having this methane up here. So it's kind of an indirect effect. So just by having some of these gases in the environment, it's not just the radiative effect of them being a greenhouse gas. They also affect the chemistry of other things in the atmosphere, which then have a kind of a secondary effect on the radiative forcing. And that's kind of really that's what the different colours in these bars mean. So CFCs, okay, you can see that's the green kind of bar on here. But CFCs, when they break down, when they react with things in the atmosphere, they particularly react with ozone. Okay, so by reacting with ozone, they're removing ozone, which is a greenhouse gas. So actually, the secondary effect of CFCs is actually a small cooling. Okay, so it's not quite as simple as just thinking about putting gases in the atmosphere, considering their radiative forcing. Is it going to get warmer or cooler? You also have to consider the effect of what happens to the chemistry of these gases when they're in the atmosphere. What else do they affect? And then what is the climatic implications of that? And that's really true when we get to thinking about these aerosols. So things like volcanic sulfate, sulfur from burning fossil fuels. These have a very complex series of interactions with the atmosphere in terms of the direct radiative effects. So if you make the atmosphere more dusty, kind of sunlight will bounce off that dust. Okay, but depending on what kind of dust it is. If it's black dust, it tends to be absorbing. But then those aerosols will have an effect on the chemistry of the atmosphere, which will affect cloud condensation nuclei, which will then affect kind of radiative forcing that way. Okay, I'll swip over this. So basically, to summarize today's lecture, so volcanoes are important in terms of a radiative cooling. El Niño, or the El Niño Southern Oscillation, kind of affects whether the average temperature of the Earth is cold or warm. It also affects the weather patterns quite dramatically. having global reaching effects. So we can pretty much explain all of the temperature rise that we've seen across the 20th century by a combination of these factors. So not just the overall rise, but some of the variability from year to year as well. We've got a pretty good handle on that. Okay.